No big difference here. So if I draw it here, you have double-stranded DNA. For example, A, G, C, T, G, C, A, C, A, for example. What is the A going to be complementary to? Shout it out.
T.
T. What is the G going to be yeah, keep going.
G.
Good.
A.
Yeah.
C.
Uh-huh.
G.
Good.
T.
Good.
G.
Good.
T.
Got it. Excellent. Now, you agree that the T and the C are bonded together.
Yeah.
Good. And these are bonded together.
Mm-hmm.
And these, and these, and these, and these. Okay, very good. These are all attached to each other. You know what I'm about to ask. What is the name of this bond? Got it. Phosphodiester bond. So all of these are phosphodiester bond linkages, right? Good. All right, let's go on and do something else. These two strands are attached to each other. When I draw a dotted line, what does that mean? Which bond? What's the name of this bond?
The hydrogen bond?
Hydrogen. Very good. Hydrogen bond. So the bond that's holding the strand is the phosphodiester covalent bond. But the bond that's holding the two strands together is the hydrogen bond. Does anyone know how many hydrogen bonds between A and T? Got it. 2. How many hydrogen bonds between G and C?
3.
3. Good. All of that should be reviewed. Good. If I write on this end 5 prime, what does that mean to you? What does the 5 prime mean to you? There's something on that end. What is it? There you go, a phosphate. The 5 prime phosphate. That means that this end is what? 3 prime, not a phosphate, but what is that? What is the name of this functional group? OH. Hydroxyl. Very good, very good. And remember that DNA is anti-parallel. So if one strand goes 5 prime to 3 prime, the other strand goes 5 prime to 3 prime the other way. Do you remember all that? Anti-parallel. So here's one characteristic of DNA. It is anti-parallel. It goes in opposite directions. Very good. Now we're going to start replicating it. What happens is this. An enzyme is going to come in. All of these things are enzyme driven. An enzyme is going to come in and break the hydrogen bonds, let's say in this area right here. Break, 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 break. And what's going to happen is that the DNA is going to bubble. So I'm not going to draw the sequence, but I'm going to draw it as a line and show you what happens after the enzyme comes in and does that. Extend the arrow here. It's going to look like this. I'm not a very good artist, so bear with me, please. Oh, that's very bad. Let me try it again. Okay, better. A little bit more symmetrical. All right. That's what's going to happen. Now, these are still hydrogen bonded. What the enzyme did is it broke the hydrogen bond between these guys here. So it bubbled out. So what is the name of this enzyme? It is called topoisomerase. Say that 10 times, right? Topoisomerase. Good. That's the first enzyme in the sequence of events. There are more coming, and you need to know all of them, and you need to know their order of appearance and what they do. And if you do, you got this whole thing. The first one is topoisomerase. It binds to this region. Now watch this. What is the name of that region? That region is called the origin of replication. That's the name of that region. The topoisomerase, which is an enzyme, recognizes that that's the origin of replication. Listen to the word. The origin of replication means that's where I'm gonna begin copying the DNA. Get it? Origin of replication. Replication means copying. And how am I gonna do it? I'm gonna break the hydrogen bonds and cause this bubble. Now, this bubble here, you can pretend or imagine as if there's a mirror in the middle. Interestingly, you'll see this. Whatever happens on this side is going to happen on this side. It's like a mirror in the middle. But the problem is this, not a problem. What happens is this, actually. What happens on this side, but it's upside down. So if this is going this way on this one, it's going this way on this one. It's a mirror image, but the image is inverted. Are we catching that? And you'll see it as we develop it. So the first enzyme that comes in is topoisomerase. Now watch this. The next enzyme that comes in is a different kind of topoisomerase, but it's still topoisomerase. Don't worry about which one it is. Just call it another topoisomerase comes in. Now this guy says this. Remembers when mom says, honey, you gotta untie your shoes before you take your shoes off. You can take it off easier. Now we never do that, we just, right? But mom would tell you, you gotta untie your shoes before you take your shoe off. Or you gotta untangle the DNA before you copy it. You can't copy tangled DNA. You gotta untangle it. And that's where this guy comes in. This guy is gonna sit here and here. Remember, whatever happens here, happens here. So if I draw it, it would look something like this. Same exact, let me try it again. Same exact structure here. With the hydrogen bonds, everything is the same. The only difference now is I now have a topoisomerase sitting here, which is an enzyme, and another one sitting here, and here's my mirror right here. Same thing. And this guy, both of them are topoisomerase, will do what? Will untangle the DNA. Untangle the DNA. Now, we have to think of, to tell you where it's sitting, where the enzyme is sitting, you actually have to say this. Topoisomerase will untangle the DNA ahead of the fork, the replication fork. So I'm going to add this, ahead of the replication fork. Let me add it in red since I'm writing in red. Ahead of the replication fork. Now, what's the replication fork? It's this part right here. Let me highlight it for you. This part right here. That's the replication fork. That means this is the other replication fork. This replication fork is going this way. This replication fork is going that way. Opposite directions of each other. So let's watch this. Listen to now, describing it. The double-stranded DNA bubbles out at the origin of replication because of topoisomerase. Topoisomerase will break the hydrogen bonds, create that bubble at the origin of replication. Another topoisomerase will come and sit ahead of the fork. To what? To do what? To untangle the DNA. Good. Then comes another enzyme. The next enzyme in line is called helicase. Helicase is the next one in line. And that guy is going to come in and sit right here and break the hydrogen bonds. So it's going to look like this. You have the untangler sitting here. And here's the bubble. And here's another untangler, the topoisomerase. And then the helicase will sit here. Let's do this helicase. and it will move this way. And here's another helicase, and it will move this way. And what it's doing is it's gonna break the hydrogen bonds. So it's breaking the hydrogen bonds as it moves. It's breaking the hydrogen. So what's gonna happen is this bubble is gonna get bigger. As the helicase moves through the DNA, it will take the double-stranded DNA and open it up. It opens it up. And it makes it single-stranded. So this guy is untangling, while the helicase, we call it unzipping. So helicase unzips the DNA. Now you haven't copied anything yet, you're just getting it ready. Okay, the next one in line is going to be a protein that's called single, it's not an enzyme, it's just a protein, stranded binding protein. Say that 10 times, right? Here it is, SSBP. That's how it's what we say, SSBP. Single-stranded binding protein. Look what that one does. As soon as the DNA becomes single-stranded, the single-stranded binding proteins will rush and bind, look, to single-stranded DNA. This protein can only bind to single-stranded DNA. If you give it double-stranded DNA, it says, I don't know what that is. I don't know what that is. But it binds to single-stranded DNA very efficiently. So it's going to do this. Everywhere where it's the DNA single-stranded, I'm going to bind single-stranded binding protein to prevent the DNA from coming back together. Because if the DNA came back together, then DNA replication stops, it's over. It's like you're preparing to paint a wall, and before you actually paint it, someone destroys the wall for you, then you don't have a wall to paint. So the single-stranded binding protein will go and bind to the single-stranded DNA to keep it open, because you don't want it to rezip. If it rezips, DNA replication is over, and you won't get a copy. All right, what's the next enzyme in line? The next enzyme in line, remember, this is a mirror image. The next enzyme in line is going to be primase. So after this happens, now this is what it's going to look like. You're going to have the DNA bubbled out. You're going to have the topoisomerase going this way. Another topoisomerase going this way. You're going to have the helicase unzipping. One of them going this way. You're going to have another helicase going this way. It's a busy thing. It's busy. And it's very fast, by the way. And you have that mirror, imaginary mirror. The next one that comes in is primase. Primase is an enzyme. It will sit right here, and another one will sit here. See, this is what I was telling you. It's a mirror image, but it's an upside down image. Whatever is happening here is happening here. And primase is going to make a little tiny, listen to this one now. Primase is going to make a little tiny primer going this way and going this way. So primase makes a primer that is actually RNA, not DNA. So look at that. The initial copy of the DNA, that small piece of primer, is actually not DNA. It's actually RNA. It starts out as RNA. It's a little tiny piece, don't worry about it, maybe 20 bases, 30 bases, I don't know. But the most important thing is that it's RNA. Now, there's another primase that will come in, because your DNA replication machinery is very efficient. It's going to start making DNA going this way, it's going to start making DNA going this way, and might as well start one here and start one here. But those two are going to go this way and this way. All the green arrows are RNA primers. Who's making them? Who's making the RNA primers? Primates. Here's the reason behind that. The reason behind making the RNA primer is, I moved this for a reason. It's not like I'm adjusting furniture. I have a reason behind it. DNA polymerase 3 is what's coming in next. The next enzyme in line is the enzyme that's actually making DNA for you. And it's called DNA polymerase 3. That's what's coming next. Oops. This guy is very good at making DNA because it's called DNA polymerase. I always ask students, what does DNA polymerase make? And they sit there puzzled. It's in the name. DNA polymerase 3 makes DNA. And it's very good at doing that. It looks at the sequence. So Eileen, when she was shouting out the sequence, she was DNA polymerase, because when I said, if I have A, what are you gonna bring in? She said T. If I have G, what are you gonna bring in? She said C. She was DNA polymerase. She said, if I read the template and there's A, I'm bringing in T. If it's G, I'm bringing in C. See? And so DNA polymerase is very good at that. But the problem is this. DNA polymerase 3, to go to work for you, it needs two things. It needs to be told where to start. See, if Eileen is DNA polymerase 3, and I say, Eileen, copy the sequence, she's gonna, but where do you want me to start? I don't know where to start. Where do I start? I don't know where to start. Nobody's telling me where to start. Primates will tell you where to start. This primer tells DNA polymerase 3, I want you to start here, 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 and here. That's what it's doing. Everywhere I put a primer, that's where I want you to start. Without this primer, DNA polymerase 3 doesn't know where to start, so it doesn't start anyway. It doesn't do anything. It says, I know how to make it, but too bad you never told me where to start, so I won't do anything. So that's one job of the primer. The primer that primase lays down tells DNA polymerase 3, hey, I want you to start here. And I want you to start here, here, and here. Okay, that's one function. Here's another function. If the RNA primer was not there, watch this now. If the RNA primer was not there, and DNA polymerase 3 says, there's no RNA primer, okay, I'll do it anyways. Let me try it anyways. So it brings the nucleotides, A, G, C, and T. Here are my nucleotides. I got them. I'm DNA polymerase 3. I'm going to copy the DNA, even though the primer is not there, which is unusual. It will not do that. But I'm showing you what would happen. I am DNA polymerase 3. I'm going to go ahead, copy the DNA, even though the primer is not there. Watch this now. I have a nucleotide. I'm going to attach it. A, T. Okay, let me try it again. A, T. I don't have anything to attach it to. That's why they're falling. I can never build the DNA that way. Unless you do this. Watch. You build the primer first. Now you have the primer. Number one, the primer tells me I need to start here. Good. And it also gives me the hydroxyl attachment point that I can say now AT and attach it. Did it fall? No. Because there's a primer there. So without the primer, DNA polymerase 3 runs into two problems. I don't know where to start. Does he want me to start here, 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 here? I don't know. So let me guess. I'll start here. And let me try to attach. Attach to what? You don't have anything to attach it to, so it falls. But with the primer in place, RNA primer, I solved this problem. The RNA primer tells DNA polymerase 3, I need you to start here. So whatever this sequence with the base is, A, bring in the T. And by the way, I got you the hydroxyl group that you can attach the phosphate group to create the first what bond? The first what bond? The first what bond? Phosphodiester bond. And now you can go to work, building the DNA. Are we catching that? So now your DNA is actually being synthesized. So DNA polymerase 3 now will extend the DNA, and it will now look like this. You'll have now the bubble again. And now, again, the imaginary mirror. The topoisomerase is still working. The helicase is still unzipping. Topo is still working. Helicase is still unzipping. And again, whatever I do on this side, that side is the same. Now the primer sitting here. Now you're gonna start building the DNA. That's DNA polymerase doing that. DNA polymerase is right here now, building the DNA. Whatever happens on this side, happens on this side. It's an inverse mirror image. Here it is. Now there's a name for this strand, which is the same as the name for this one, and that is called the leading strand. It's made in one continuous motion. So the leading strand, DNA polymerase 3, sits here and goes like this. Copy, 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 until it falls off. It's made in one continuous motion. It doesn't stop. It makes it in one piece. Let me do it again. The DNA polymerase 3 will sit here and start copying, and it will copy as the DNA is untangled and unzipped. Untangled, unzip as it's copying. It's amazing. It's really, really fast, actually. And whatever is happening here is also happening here, remember? Because it's made in one continuous motion, it's called continuous replication there. One piece. And the name of that strand is the leading strand. Now, I can't say the same thing about the other one. Remember, look where the primer is in the other one. The primer is sitting here. So the new DNA is going to be built this way. This primer is sitting here. The new one is going to go this way. DNA always builds 5' to 3', the 5' to 3' direction. So the DNA is building 5' to 3' this way, 5' to 3' this way. All nucleic acids are built in this direction, 5' to 3'. So it forces this sequence, this one here, to be built in pieces. Watch this, watch. As it opens up, a new primer will be built, and then another piece will be copied. As this opens up, a new primer will be synthesized, and another piece will be made, again, going this way. So look at the difference. This one, the leading strand, is made in one continuous motion, in one piece. This is called, maybe you heard it before, the lagging strand. That's made in pieces. Does anyone know the name of the pieces from your previous biology life? You didn't hear about Dr. Okazaki riding a Kawasaki?
Oh, the Okazaki.
That was a joke, by the way. Anyways, Okazaki fragments. It's called Okazaki fragments. These are Okazaki fragments. Meaning they're made in pieces. So what's the opposite of continuous? Discontinuous. So the word discontinuous means made in pieces. So the leading strand is made in one piece called the the leading strand is made in one piece, and that type of replication is called continuous. Because the pieces is called discontinuous, and the fragments are called Okazaki fragments. We're not done. Got 2 more enzymes to talk about. The next enzyme that comes in play is DNA polymerase 3's cousin, DNA polymerase 1. DNA polymerase 1 realizes something. I know primase laid down the primer so that DNA polymerase 3 knows where to start and has the hydroxyl group for the attachment. Good. DNA polymerase 3, DNA polymerase 3 required the primer to build the DNA. Are we okay so far? Now DNA polymerase 1 realizes something. DNA polymerase 1 is the next one. It's DNA polymerase 3's cousin. It realizes something. Oh, I don't need the primer anymore, because it already did its job. This RNA primer already did its job. It provided the start site, the start of the replication, and the attachment point. So the DNA is already building 5' to 3'. I don't need this one anymore, so I'm going to do this. I'm DNA polymerase 1 now. I'm going to do this. I'm going to come in, remove the primer, and I'm going to replace it with DNA. So at the end, it's all DNA. So DNA polymerase 1 will now come in and replace the primer, which is RNA. Replace the RNA primer with what? What did I say?
DNA.
With DNA. Good, we're still not done yet. At the end of all of this, your DNA will now look like this. It will have a piece and another piece, especially, of course, the Okazaki fragments. The leading strand is made in one piece, remember that. Especially the Okazaki fragments, you're going to have that link that's missed, that little tiny seal that's missing. You have the two fragments, but it's not linked. They're not linked. You have to create that final phosphodiester bond. And there's an enzyme for that one. DNA ligase. DNA ligase will come in and create that phosphodiester bond. Now you have a full strand. So it's sort of like this. You have one strand and you have another strand. You're missing that gap is the final phosphodiester bond. DNA ligase will come in and they will do this. Now you have a full strand. So at the end, all the Okazaki fragments will seal and it will look like the leading strand, one continuous piece. The primers are gone, it's all DNA, and it's all linked together, it's made in one, it becomes a continuous piece. You won't know the difference between that one and the leading strand at the end. So look what happens at the end. At the end, what happened is you separated these two strands. And you copied this one, and then you copied this one. So at the end, it will really look like this. Watch. The green color is the original DNA strand, okay? The black one is going to be the new one. At the end, you will have, well, now it's red. No, let me make it black. The black one is going to be the new one. So this will be TCG, ACG, T, what is that? C, yeah, G, T. And if this is 5', this will be what?
3.
3'. If this is 3', this will be what? 5. And again, everything will be phosphodiester bonded. And these will be hydrogen bonded. All of them. And then you'll have the other copy. Every T, there's going to be an A, C, G, C, T, G, C, A, C, A. Am I right? Yeah. If this is 5', this is 3'. If this is 3', this is 5'. And I have the phosphodiester bonds. And I have the hydrogen bonds. Look what I did at the end of this. Look at that. I have 2 copies now. I have this and this. Now I have 2 copies. But there's something interesting at the end of this. The product. Look at the product. This is a product, and this is a product of DNA replication. Look at it. 1/2 of the product, a half of the product, is the original strand. The other half is what I just made. Now look at the counterpart. The other molecule, this is the original strand. And the other half of that is what I just made. What kind of replication is that? What is that called? Semi-conservative replication. All DNA replication is semi-conservative, all of it. which means at the end of DNA replication, the molecule, the copied molecule, will be half parental, half new. So what really happens in DNA replication, if you look up here, please, is this. You have two strands, they're opposite in direction. Watch this, 5' is my elbow, 3' is right here. The other strand is this way because DNA is anti-parallel. And here's copying of the DNA, the easiest way to copy DNA. Open it up, copy this, you're done. That's semi-conservative. When you open it up and you copy this, what it means is at the end, you're gonna have one original and one new. And then you're gonna copy this one original and one new. That type of replication is called semi-conservative. And all DNA replication is like that. It is semi-conservative, all of it. So look at all the characteristics of DNA that we did here. DNA is anti-parallel. That means it goes in opposite direction. We gave you the name of the enzymes that are involved in DNA replication. In the middle of that, we defined and described what leading strand is compared to lagging strand. We said that DNA replication on the leading strand is continuous. DNA replication on the lagging strand is discontinuous, means it's made in pieces. The name of the pieces, Okazaki fragments. To seal the pieces, we're using DNA ligase. See that? But at the end, the product, surprise, half new, half old. What do we call it? We call it semi-conservative. So let's do a quick review of the enzymes. And I need to hear it from you now. And try to do it from memory. Don't look at your notes. Don't look at your notes. You'll be surprised how much you already remember. Besides, it's on the board. Okay? What's the first enzyme that comes in line? Topoisomerase. What does it do? The first one, the first topo. Not the first topo. It creates that bubble. Good. It opens up the origin of replication. Sounds good? What about the next enzyme? What's the name of the next enzyme in line? Topoisomerase. Good. What does that one do? That's the one that untangles the DNA. Untie your shoe before you take your shoe off, kind of thing. All right. The next one in line. Helicase. What does it do? Unzips the DNA by breaking down which bonds? Hydrogen bonds. What's the next enzyme in line? The single-stranded binding proteins. What does that one do? It prevents the DNA from becoming double-stranded. Very good. It keeps the DNA single-stranded, which means it prevents it from becoming double-stranded. I mean, it's like a zipper, right? If you unzip your zipper and then somebody zips it up on you, then you're not getting out of your whatever clothing, right? You're stuck in your clothing, see? Because that's why they actually call it unzip your DNA, because it almost looks like a zipper here. And if you look at biology books, they draw it like as if it's a zipper there. So helicase unzips your DNA. It opens it up, that means breaks down hydrogen bonds, but you gotta keep it unzipped. You gotta keep it single-stranded, and the single-stranded binding proteins do that. Okay, then what's the next enzyme in line? Not polymerase yet. Primase. It lays down what? The RNA primer. What does it do? What does the RNA primer do? It tells DNA polymerase III where to start, and it provides it the attachment point. Am I right? So that means DNA polymerase III is the one that's actually making the DNA. Now you're making DNA. Okay? After the DNA is being made already, do you have any more use for the primer? No. Who removes it? DNA polymerase I removes it and replaces it with what? With DNA. Very good. And then who finally seals the gap? DNA ligase. I didn't write that, sorry. DNA ligase. It is the final enzyme.